Hello everyone and welcome to the Huygens Scripting with Python webinar. My name is Kiefer van Teutem and I'm a developer at SVI. Today we're going to be looking at the Python interpreter, the Python shell, what you can do with it, how you can use it to perform image operations, and also how you can write your own scripts and load them in Huygens. We're going to be looking at a lot of examples, so you don't necessarily need to already be familiar with Python, but it does of course help. Now, before we begin with an explanation of Python itself, I want to show you a fun little example that shows the power of the Python scripting. So let's hop over to Huygens Professional. Alright, so I've already prepared a little script that'll generate a simple 3D fractal. So let's have a look at that. So in order to load that script, we can simply specify the path like this. And let's see where it is. Yes, I call it menger.py because it will generate a menger sponge. Don't worry about the syntax for now because we'll be going over that later. Alright, so that generates 4 images, and those will be separate stages of a menger sponge. And as you can see, it kind of starts generating this 3D fractal. I can show you the script later, but basically it's just a 30-line script that copy and pastes images to create this sponge. And we can open it in the SFP renderer, and here you can see the sponge in all its glory. Alright, so now that we've looked at that fun little example, let's actually dive into how to use Python and the Python interpreter. So first, what is Huygens Python scripting? Well, first of all, Python is a very well-known scripting language that you can use to perform all kinds of calculations and operations. And recently, starting from Huygens 20.10, Huygens 20.10, we've included the ability to use Python and special Huygens Python operations to perform image operations. So the Python shell and Python scripting is included in Huygens Professional and Huygens Localizer, as you can see on the left here and on the right here. So the simplest way to use the Python interpreter is to use the so-called shell. So in Huygens Professional, you can find the shell in the main window by simply going over to the right and clicking Python shell. And in the localizer, you can find the shell in the bottom left by clicking on this localizer scripting button, and that'll open a new window which will give you a shell. As you can see, maybe over here, there is also a Tcl shell. Now, if you don't know what Tcl is basically just another scripting language that we've used in all previous versions of Huygens to allow you to perform image operations. And of course, the Tcl shell is still fully functional and fully usable. So simply by clicking on Tcl shell or Python shell, you can keep switching back and forth between the different shells and perform operations in whatever language you'd like. So basically, the Python shell is just the Python version of the existing Tcl shell. So all the image operations that you may have been familiar with in Tcl are still available in the Python shell. But of course, in Python you can also use the standard libraries, and I'll show you later how to include additional Python libraries as well. So let's look at a first sort of real example. we won't be focusing on the syntax as much still, but here you can see a little bit of what you can do with the Python shell. So as you can see, this is a shell box. You can literally just click here and type commands, and if it's a command that has a return value, it'll immediately return that and print it right below your command. As you can see here, you can type 2 plus 3 and it will give you 5, and you'll just immediately get a result. You can perform all the standard Python operations with list and list indexing and stuff like that. Here at the top you can see two simple print operations. The top one uses who_opt, which is one of the kind of special methods that we'll get into later. And we also have the regular Python print, which will print directly to the shell here. So all the operations over here are fairly trivial, but probably the most important part of the Python shell is being able to open images and perform image operations. So here in this first line, or line 8, we see that we are creating a new image, and that is done by creating a so-called image object. So we simply type image, and then in parentheses we type a new image name, and that'll create a so-called image object, and we can assign that image object to the PSF variable, and that'll create this new image in the top left over here. Then we open an image from file, and we're going to call that orig for original, and you can see that you can simply specify the path as a keyword argument to the image class, and that will allow you to open this image. And then in the third step we actually perform a simple deconvolution operation with standard parameters by using the CMLE command, classic maximum likelihood estimation, on this original image. As you can see, the operation appears as a method of the image object, or you can simply think of it as you can take your image object, add a dot, and then you have to insert the operation name. So here we perform a simple deconvolution with this PSF image and 40 iterations, and that'll be assigned to this result image, and you can see that over here. So we'll go over some more specifics of the syntax later, but this is just to show you what you can do. You can open images and perform deconvolutions and all kinds of mathematical operations and save images. So basically we have the standard Python syntax and operations, and as we've already seen, we have this new image object which is unique to Huygens, and for the localizer, which is a special SKU of Huygens, which is specially made to deal with single molecule localization microscopy images, you also have to be able to work with localization tables. And so for those we have the so-called table class, but we'll see that a little bit later. So the most important parts are the regular Python operations, the image and the table classes, and then some special classes like who_opt, which we saw earlier for this report operation, that are basically used as bundles of additional miscellaneous operations. Now, one of the useful things to note about the Python shell is that you can, of course, type commands and just execute them by pressing return, but you can also use the arrow keys to go to previous or next commands, and you can press tab to autocomplete image operations or options, or to get a list of possible options that you can use for a specific operation. Alright, so let's have a closer look at these image objects and how to create and destroy them. there are several different ways of creating an image object, and the simplest way is to simply say something like a equals image, and then in parentheses you can give the name for the new image, and this will create an image and put a reference to it in A, and the title of the image will be this string new image. This string is actually optional. If you don't provide it, you'll simply get an image called default, and then you can use that. You can also specify extra options like the dimensions you want for your image. As you can see here, that would be a keyword argument. And another example we see here is the number of channels that we want for our image. There are other options like the data type and stuff like that, and you can find that in the scripting manual. So that's one way of creating an image. That's just creating a new image. Another way is to adopt an image from Tcl or the main window. Now this can be useful because not all images may have been created from the Python shell. An image may have been generated in a Huygens tool or been opened using the Huygens main window, or created in the Tcl interpreter, for example. So if you have an image and you know its name and you want to be able to access it in the Python shell, you can use something like this. You can say c equals image, and then you say Tcl name equals, and then the literal string of the image name, and that'll give you a reference to an image that already exists for which you know the title of the image. And then finally, of course, you can open an image from disk by again creating an image object and then specifying the path as a string. So that'll open the image and give you an image object that refers to it. So as I've mentioned, these image objects should be seen as a reference to an image. So you can have multiple references to the same image, and that won't actually mean that you have multiple copies of the image or that it will cost more memory. And the way that Python garbage collection works is that you generally don't have to explicitly destroy images. You can simply destroy the references to the image, and then once the last reference is destroyed, the image will be deleted. So what does that mean? Well, I can explain based on this example over here. So first we see e equals image. So this is the simplest way of creating a new image. Alright, this will be a new image object and it will be assigned to the variable e. Later we could have some step where we have some new variable and we set that equal to e. Now this simply means that we will get another reference to the same image object, so we won't actually get a copy of the image. And later on we might even have a third copy, g, and that might come from f. So at this point, after these three lines, we have an image and we have three different variables that refer to that image, like e, f, and g. Okay, so now what would happen if we set e equal to 7? So instead of having e being that image object, e is now equal to 7, which means that one of the references to the object has disappeared, but we still have the existing variables f and g, which refer to the image, so the image still exists and nothing happens. Another way that a variable might get overwritten or deleted is by explicitly deleting the variable using the built-in Python del command, which will delete any object. So here we have del f, and that will delete the variable f, which also means that we now only have one remaining reference to the original image, which is stored in g. So up to this point nothing has happened to our image, but then if we set g equal to 6, for example, the last of our references has disappeared and the image is destroyed. Now this is something to look out for. It's very handy because you have automatic garbage collection, but at the same time, if you want to keep an image around, if you want to still be able to perform operations on it later, you need to make sure that you still have a variable with which you can access the image. So now that we know how to create and destroy images, let's look at image operations. So image operations appear as methods to the image class. So once you have assigned an image to a variable, you can perform image operations by simply taking that variable and then doing dot and then the operation name. So for example, if we have an image called orig and we want to perform a Gaussian blurring operation, we can do orig.gauss, and then we have to specify the name of a new result image, and optionally we can also specify some extra arguments, so in this case the sigma of the Gaussian blurring. So the general structure of these operations is that you have image dot operation, and then you have some positional arguments which may or may not be mandatory. These are usually things like a result image or mandatory auxiliary images, and then there's a whole bunch of additional options that appear as keyword arguments that just specify more properties of the operation. So once you perform an operation, of course the operation will take place, but depending on the operation you can also get a result image back, or some values. For example, in this range command you can get the value ranges of the voxel values in an image for each channel, and here you can see you get a Python list with some strings and some values in it. And there are certain operations that even return a result image and additional information, and in that case it'll be returned as a tuple of both a destination image and some additional results. So that will be the general structure of image operations, and it's useful to remember that you can always press tab to see what operations are available and what options are available. There are a lot of operations which either require some auxiliary images or which may have a destination, and you can specify these auxiliary images and destinations in several different ways. So for destination images, for example, you can completely leave out the destination, in which case a destination will automatically be created with the same name as the operation that you're performing. Another option is to only specify a string, which means that you still get a new destination image, but its name will be the string that you have provided. Or you can specify a direct image object for your destination, in which case that image object will be used as your destination. And for auxiliary images, it's mostly the same. You can either specify an image name or an image object, except if you specify an image name for auxiliary images, it has to be an existing image in the main window or in the Tcl interpreter. So if we look at this example, here are 3 different ways of specifying destination and auxiliary images for the CMLE restoration command. And we can see that the syntax is CMLE, then a PSF image, and then a destination image. And we can see that we can specify the auxiliary PSF image using a string or as an object, and we can specify the destination as an object or as a string, or leave it out entirely as in this first example. So there are many image operations and options, and if you want to find out which ones are available and how to use them, the best way to find all of them is to look at the scripting manual, which can be found at svi.nl/manuals. So one of the nice properties of these image objects, it's that you can use them directly in mathematical operations. So here we can see a simple operation where we set all the voxel values in an image to 5. So A will be an image and we do a.set 5. So every voxel in the image will be 5. But then we have these special overloaded operations where you can treat the images, so A, B, and C here, as if they are numbers. So in this example, we take an image A, we subtract an image B, and divide it by 2, and put the result in C. And this will just be performed on a voxel by voxel basis. So yeah, for each individual voxel, this operation will take place. What you can also do is directly access the voxel values in an image, and you can use this either by linear index or using a position in the image. So for example, here we have an image A and we want to set the voxel at linear index 32,767 to 7, and we can do that, and we can also request its value by simply typing it, and then we get a result. And here we can see an example of using a literal position in an image and using that for a voxel multiplication. And one of the nice things about the image objects is that they are also iterable, so you can use standard Python syntax to loop over images. So in this example here, we have for index in A index is index 1. And what this will do is, since this index will by default give you a position, this will be a multidimensional vector, and the first element of this vector will be the y position in the image. So what we're doing here is we're setting the voxel value of each voxel in the image equal to the y position of that voxel. So that'll mean that you'll get a simple smooth gradient in the y direction. Now of course this isn't very useful, but in general you can do all kinds of complicated operations in this way. And finally, at least as far as Huygens Professional is concerned, it is very useful to be able to write your own scripts to a file and then be able to source those scripts. So the way you do that is quite simple. You create a new file in your favorite editor. You simply write out all the commands that you want to use, and then you can save that file, and then you can source it in several different ways. And each time you source the file, all the variables will exist in the Python interpreter, and all the operations will just be performed one after another. So there are 3 different ways of sourcing a script. You can either launch Huygens from the command line using Huygens Pro or Huygens Loc or Huygens Core, and then you can directly specify the path to your Python script, and that'll launch Huygens and directly perform the script, and then optionally exit or close Huygens if you want. So for example, here we have a script that has an exit command at the end, and that means that after the script has finished, Huygens will be closed. So this is the most raw way of running a script, but you can also open Huygens Professional or Huygens Localizer, and you can go to File and then Source Python Script or Source Tickle Script, but in this case we're looking at Python, of course. And that'll source the script directly into your Python shell. And finally, as we've already seen in the example that I gave earlier, you can use the function source and directly provide the path to your script to source the script. Alright, so now that we've looked at all the different image operations and all the different things within the Python syntax, let's go back to Huygens Professional and try some of these things out for ourselves. So here we have Huygens Professional, and let's first just try to create a new image. So that will be A equals, and then just image, and then we can open and close some parentheses, and then we will get a new image with a default name. As we can see, it pops up right here. But if we wanted to, we could have also created an image, let's say B, with a new name, let's say B image, like this, which is simply specified as a string, and then we have a new image called B image. So as I mentioned earlier, one of the things to watch out for in the Python syntax is that once all the references to an image get destroyed, the image itself also gets destroyed. So for example, if you type b equals 7, we will be overriding the b variable and the b image will disappear, like this. Okay, so let's try something more interesting. Let's open an image and let's call it dendrite, and let's say dendrite equals image, and then open an image from path. So we say path equals, and then I have it on a flash drive, so we can start typing the path. Now one thing that's very useful is that you can simply press tab once or twice, and it'll start auto-completing options and also give you extra options once you press tab for the second time. So here we actually get a list of all the possible files that we might want to open, and in this case I want to open this ICS image file. There we go, and let's open that image. Alright, so now we have this new dendrite image, which is also called dendrite in the Python interpreter. And if we wanted to, for example, perform a restoration command on this, we would simply type dendrite, which is the Python variable dot cmle, and then we have to specify a destination, or no, we have to specify a PSF and the destination. So the PSF can simply be this image, this default image that we've used, which is empty, and we could do this in two different ways. We could literally type default as a string, which would try to load this image from the main window using its name, or since we've also assigned this image to the variable a, we could also use a, and that would do the same thing. Now theoretically this should be enough, but we could also specify the new name of our destination image. Let's call it dest, and let's say we want to use 5 iterations because it's just a simple test. And if we want to use this image later, it's also useful to assign it to a new variable. So let's say new equals the result of this operation. So there we go, a destination is created with the name dest, and the deconvolution is being performed, and here we go. We have a deconvolved image, which is already a lot clearer than the original, even after 5 iterations, which is nice. And it is stored in our new variable. So one of the things that we might want to do is perform a Gaussian blurring operation on this new image. So we would simply do new.gauss, and then we have to specify a result image. So maybe we'll try to put it in this default image, so we can just simply specify default like this, and that'll perform a Gaussian operation. And we can specify extra options such as the sigma of this operation, and let's say that we want a sigma of 3 in each direction, and the units we want to use for this are samples, which will be s, like this. Yes, of course. So this is a this is a destination image. So if we specify a string, it'll create a new image with this default name, but this default name already existed over here, so we get a new image called default 0. So let's delete this and try it again. If we actually wanted to put the destination of this Gaussian operation and have it be default, then we'd have to actually specify the image object. And the image object was A for this default image. There we go. Now we have the result of our Gaussian blurring operation in the default image. Alright, so that's probably enough of a demo for now, and let's continue with some different features of the Python interpreter, and let's look at using the Python interpreter in the Huygens Localizer. So as I mentioned before, the Huygens Localizer is a special branch of Huygens that is specialized in dealing with single molecule localization microscopy images. So what that means is that you have an image with spots which are turning on and off, and these will be single fluorescing molecules, and by recording a time series of these flickering molecules, you can determine the position of each of these molecules and use that to generate an image with a much higher resolution than you would be with regular optical microscopy. So one thing that's very important for this localization microscopy is performing the localization and getting the position and properties of all of these fluorescing molecules. And so these properties can be determined by Huygens, and you can perform the localization in Huygens, and then you'll get something called a localization table. So as you can see over here on the left, we see such a localization table, which is the result of running the localizer wizard on this original SMLM image. And here we can see for each frame of the original image, we have a bunch of molecules that have been found, and they all have an intensity and an XYZ position and a full width at half maximum value, etc. So we get a big table for every single frame of the original image, and the thumbnail you see here is actually a rendering based on this table. Now, to be able to use scripting in a useful way in the Python localizer, it is necessary to be able to manipulate these tables just as you are able to manipulate the images in Huygens Professional. And to do that, we have a so-called table object, which directly mirrors the image object that you have in Huygens Professional. So, for example, you can create tables from scratch, open a table from file, or adopt an existing table from Tcl, and that works in exactly the same way as it does in Professional, except here we see, for example, A equals table instead of A equals image, and here we have a new image named foo. And when creating a table from scratch, it's useful to specify all the different columns that you might want to use. So these will be all the properties of the molecules that you want to record. And here we can see an example of opening a table from file, and finally we can see an example of adopting a table from the main window, as we've already seen. Here you can see that you can find the localizer scripting window by simply clicking this localizer scripting button, and it will open a little pop-up window that will give you a task report window and a Python or Tcl shell, just as you have it in Huygens Professional. So there are many table operations just as there are many image operations, and they work in the same way as for images. You simply type your table variable, then dot, and then whatever operation you want to use. So for example, this would be a copy part command, which allows you to copy a part of a table to another table. So this would copy a piece of the table B to an existing table object A, and that would have a source offset, a destination offset, and a span, and these numbers will be a channel range, and a frame range, or rather a channel position and a frame position. Now you can directly access the table values as well. You can simply use your table variable and use either a linear or positional index, just like you can do it for regular images. If you use a linear index, it is assumed that you simply want to specify the frame, and you'll get all the localization information for frame 31, for example, and that'll be returned as a direct list of lists of values, where every list will be a list of properties for one localization, and then if you have multiple of those, that just means that you have multiple localizations for this frame. And this can be used to set and get and filter localization information. The table objects are iterable, just as they are for images, so you can loop over the tables and do stuff like copy part of a localization table to another table, but now explicitly, and you can use this to, for example, filter values in a table and get a new filtered result. So as I mentioned, you can use this index linearly, in which case it will simply be the frame, but you can also use two variables, and if you do that, it will be a channel and then a frame. But in most cases, localization images will only have one channel, so you can just specify one number and it will just be the frame. So here in this example, we can see a simple filter operation where we can say for each frame in localization table A, we can set all the localizations for this frame equal to the localizations in this frame for which the intensity, which is the first element of each localization, is smaller than 10,000. So you'd simply filter out all the localizations that have an intensity greater than 10,000, because those are not in this selection syntax. And finally, you can save tables just like you can save regular images by using the save command, specifying a path and then a type. Now these are just a handful of operations that I've shown for the tables, but there are many more, just like for images, and you can find detailed information about these operations by going to the scripting manual, which can be found at svi.nl/manuals. So finally, what you might want to do in the Python shell or the Python interpreter is to use different packages. So there are a number of Python packages like sys or math or complex math, which are default packages, and you can simply import them like you would by using the Python import syntax, and you could simply import math or import cmath or something like that, and that'll work automatically. But if you want to use some more complicated modules or libraries, you can adopt them from another Python installation. So if you have your own Python installation on your computer, or you're using something like Jupyter Notebooks, you can simply go to that Python installation that you have. You can run it. You can import the module that you want to use in Huygens. So you're importing it in your Python distribution of choice. You can import the module that you want to use, and then you can use that module __path __, and that'll actually give you the path at which that module is located. And if you add this path at which the module is located to your Huygens preferences under directories Python module paths, then after you do that and restart Huygens, Huygens will actually be able to use the modules that are located there, and so you can directly use the modules from another Python installation in Huygens. Now for some modules you may require multiple module paths, because the modules will have dependencies which themselves have different paths. And if this is the case, if you try to import the module, you'll get some sort of dependency warning, and you'll have to go back to your original Python version, or the Python from which you want to adopt a module, and find out what the path is for that dependency module. So if NumPy depended on math and math was not a standard library, you might get something like, oh, I'm trying to import NumPy but I can't find math, so then you would import math as well, do the same dot underscore underscore path to find out the math path and add that here, and then you should be able to import NumPy. But as it stands, NumPy only requires one path, and then you'll be able to use it in Python. So I hope that's clear. It can take a couple minutes to find these paths for your modules, but after that you can save them in your preferences and you can use them whenever you want in Huygens, and even when you reinstall Huygens or upgrade to a different version, those preferences should stay. So you can use the packages forever. Alright, I hope you've learned a bit about the Python shell and the Python interpreter and how to use it. There are a lot of different options, so I really recommend going to our website and going to Python Huygens if you want to delve into it a little bit deeper, or if you want to find out more about specific image operations, you can download the scripting manual and find all the options and all the image operations and table operations that you can perform. If you'd like to try out Huygens, you can go to svi.nl/license request over here. And if you have any other questions, you can send them to sales@svi.nl. Thank you for watching.